All right, friends, we're starting into Maxima and Minima, which collectively are called Extrema. And this has to do with something else called critical points, so those are all kind of bundled together. So we'll talk about all of those right now. Um, just basically, if you want the simple definition, extrema are, for the most part, they are either peaks or valleys. If you were to look at a graph, um, you can certainly just graph it on Desmos or on your graphing calculator, and you can answer many of these questions. We're going to look at the mathematical version of this, which is obviously can be a little trickier, but you're not locked into one method or the other. So just whatever you're comfortable with, my friend. So first of all, these maxima minima can be divided into either absolute, my little typo there, or local. Absolute meaning that over the entire graph from whatever we're looking at, from positive infinity to negative infinity, that point is either the lowest in the case of a minima or the highest in the case of maxima. Local just means in a little area. That's just the little peak, the little top of the hill, bottom of the valley, that kind of thing. Importantly, we have critical points, which, remember, extrema and critical points aren't necessarily the same thing, so we need to be careful. We do not use those words interchangeably. Critical points have the following definition, super important. One is it's any point where the first derivative of the function is equal to 0, meaning the slope is horizontal, which would be the case at all the maxima and minima. You would have a horizontal slope. Also, though, we have this f of x is undefined, and that can happen for lots of different reasons, but for example, if you have a vertical slope at some place, you have an asymptote, you have like a cusp or something like that. There's lots of different ways that you can create this undefined situation. That point, when you find it, it is a critical point if you find an undefined first derivative somewhere. However, it does not have to be either a maximum or minimum. It can be something else. So just know that. It doesn't have to be one of those things. So let's look at some examples here of how we're going to work with this. First of all, just some quick visuals here. So in this case, you see there's the top of a peak here. If I look at point C, right, that this would be the derivative there. The slope is flat, and so that would be a max. If this is the entire curve, like an upside down parabola, that would be a global max or an absolute max. Over here, we see we have like a cusp here, this kind of a situation. This is one of those undefined situations. In this case, the undefined situation does not mean it isn't a max. So the slope is not 0 here, but it is also a max, so it can be or cannot be. In the case of something like this, where you have the graph goes up and it has a little peak here and then it comes down, we'd have 2 points. We'd have a local max here at, I've marked this as C. We'd have a local min there. I've marked that at D. I'm sure you get the idea. We don't need to go on too much farther in that. So let's look at some examples of how to do this mathematically. So here, first of all, these problems are usually given by just the instructions, find all critical points. So you're given a function, and in this case, here's our function right here. And so step one, obviously, is you're going to need to take the first derivative. We need to take the derivative so that we can find the critical points. So in this case, I take this derivative here. Fairly straightforward, nothing weird going on here. And then I see that this is a quadratic. So remember, I'm going to set this thing equal to 0. That's the key here. So find the derivative, set it equal to 0. Find the x values where it's true. So in this case, this is fairly simple to factor. And so I find that I have 2 critical points, one at x equals 1 and one at x equals 4. So obviously, if the question, because sometimes it says how many critical points are there? That's a legitimate question. In this case, you'd say I have 2, one at 1 and one at 4. And then it might say to classify them, whatever. In this case, it just said to find them is all it said. So there they are. They're right here, 1 and 4. But let's go a notch further, and let's just pretend that it said to classify them. So meaning I need to decide, what is this? Is it a min? Is it a max? Is it local? What is the case? What's going on here? So first of all, we note the kind of graph that this is. This is a cubic equation. So I know that it's doing something. It's doing the John Travolta, right? It's going up or down, one of those things. So what we do is we're going to take these test points here, and you can see that I've indicated, here's 1 and here's 4. So I want you to think for a minute, if it's a max, in other words, if the curve is at a max, and I'm just going to sketch this over here. So imagine that here's my critical point here, right? And it's a max. And I were to look at the slopes on the left side of that point, wouldn't the slopes over here be positive slopes? I don't know what the value is, but they're going to be positive slopes. And if I look on the right side of that point, wouldn't they be negative slopes? Right? So then if you test a value on the left and it's positive slopes, test a value on the right and it's negative, then that tells you that that point is a max. Conversely, if we do the other way around, I think you can figure it out. If I find a point and I test on the left and they're negative slopes, test on the right and they're positive slopes, that means it's a min. Okay? So we can we can look here and say, I'm going to find some test points. Now, I've written them in red. So remember, these points right here, 1 and 4, those are our critical points. So we know that the slope here is 0. So I'm going to look at the slope. I'm actually going to look at this equation right here. I'm going to look at the slope to figure out what is the slope on the left of this point 1. So we're going to pick a test point. Let's pick an easy point, friends, like 0. So when you plug 0 into our derivative, 0 minus 0 plus 4 is, and I don't care what the value is, I just care, is it positive or negative? That's all we're looking for, positive or negative. In this case, when you put that in, you see that the value is positive. Right? My assumption then is going to be that since the left side of this critical point is positive, it's this example, right? Meaning, when I pick a point here, I'm going to bet you it's going to be negative. But we want to double check because there are some situations where that's not the case. It's not going to be the case here because this graph won't generate that. But it could be if you were having a graph that you didn't know what the nature of it was. So let's test. We're expecting it to be negative. So I'm going to pick a point in here. Any point in here will do. Let's pick 2. So if I put 2 in here, I'm going to get 4 minus 10 plus 4. Well, 4 plus 4 is 8. 8 minus 10 is negative 2. So the answer is negative. And again, we don't care what the value is. We just care whether it's negative. Aha. We suspected this. So then we can say that this critical point is a max, right? Now look, this point, this test point was the right hand for this critical point, but notice it's also the left hand for that critical point, right? So then probably we're heading into this situation here. So if I test 5, another test point, I just picked 5. You can pick any number you want and put it in here. If I put in 5, I get 25 minus 25 plus 4, and guess what? It is positive at that value. So this is a min. All right. And are these global or local? Global. I say global. The book says absolute. Doesn't matter. It's all the same thing. Are these meaning, when I say absolute, meaning is this point the highest point anywhere on the entire graph? Is that point the lowest point anywhere on the entire graph? And the answer is no. This is a cubic equation. This goes off to positive infinity as I go to the right, and it goes off to negative infinity as I go to the left. So these are both locals. These are both local. Local max, local min. Okay? We're going to look at some more examples here. So let's look at a different one. Here's x squared minus 1 cubed. So again, step 1, take the derivative, and I get this right here. This is a chain rule, right? So bring the 3 down, change that to a 2, take the derivative of the inner function. The du is 2x. And I'm going to go ahead and simplify this a little bit here just so it's easier to look at. Now, step 2, set this equal to 0. And you see this is going to generate 3 critical points. So I'm going to get a x equals 0 point here. I'm going to get a 1 and a -1. So I have 3 critical points. Again, how many? 3. Where are they? They're right there. So let's go ahead and test, right? So remember this equation right here, this equation is the derivative. So we want to test our regions. So notice I have 3 critical points, which means how many regions do you get? Well, I get 1, 2, 3, 4 regions. So we need to test things in those 4 regions. So then let's pick a value over here. I'm going to pick -2 for my first region here. So when I plug in, and remember, we're only looking for the sign, right? Now look, let's be sneaky here. My friends, look here, please. You see that that's a squared? So whatever I put in here for x squared, this is going to make it positive. Positive -1. Even if you put, like, let's say 0. Like when I put 0 in here, this would be -1, but it's going to square it. So it doesn't really matter what you put in here. This entire value is constantly going to be positive, no matter what you put in there. So we don't need to actually evaluate this part. That part is always going to be a positive. So the only thing that's going to matter is this part, right? So if I put -2 in there, that's going to be 3. 3 squared is 9. Again, that part's positive. We don't care. We don't care about this. We do care about this. So when I put that in here, -2 in here, I get -12. And so the answer is negative. So this side of that point is negative. Now, oh no, sometimes we have to use fractions here. Very, very irritating, my friends. Let's do -1/2. Again, this does not matter. We only have to plug it in here. Oh, look here. Look what that does. This is also negative. What happens then? What does that mean? Well, we're going to discover later on what to do about that situation when that happens. Don't worry about it for now. Just know that right now, that's not going to be either a max or a min. It's something else. Because remember, we talked about that you can have a critical point that's not a max or a min. So this is doing something different. Now, let's test over here. Let's test at 1/2. If I test at 1/2, this is now positive. Aha. So I couldn't tell you what this is because this is negative, but I can tell you what this is. Negative on the left, positive on the right. That means this is a min. And then over here, I'm going to put 1 in here. Let's put 2 in. Oh, and look, it's +2. So these 2 points are doing their own thing. I don't know what they're doing, but I do know that this point is a min. So I would put just I don't know what these are, right? They don't pass this test. It's called a first derivative test. They're not passing this. So, and that's okay. We don't, we're not worried about that. But we can classify this as a min. Okay, and let's see. Let's look at one other here. Ooh, here's a rational expression. Ooh. So we got to take the derivative. Looks like we got to use the quotient rule. Did it here. Now, we're talking about setting this equal to 0, and this is a fraction. So we do need to worry about if the denominator goes to 0, because then it's undefined, which is also a critical point. Remember, if the first derivative is undefined, that too is a critical point. But look here. There's nothing I can put in here. There's no x value that will turn this into a 0. So we literally can ignore that. There's no undefined. Then we only have to look at the numerator here. When is the numerator 0? Because that's when a fraction equals 0, is when the numerator equals 0. So I rewrote it over here, and I did some simplification, and I got it to this. So this is the numerator here. And set it equal to 0, and so we found 1 and -1. There's our values. And so then we can do our testing, right? So let's pick -2, let's pick 0, let's pick 2. So, and we can just look right here, because remember that, again, this is squared, so this denominator is always going to be positive, so it doesn't factor into any of our thinking. We only need to look at this value here. So when I plug in negative 2 squared is positive 4. 1 minus 4 is negative. So over here at this test value, that's negative. When I plug in 0, 1 minus 0 is positive. Aha! That's more like it. And then back over here is negative. Very straightforward. Negative to positive. Negative to positive. What is this? That means this is a min. Positive to negative. What is this? This is a max. And sometimes we can't tell if they're global or local just by doing the math. There's some trickier ways to do it. You can just graph it if you really need to know that. It's not a critical thing whether you say, unless the question is specifically asking, describe whether it's global or local. Then you can dig into that. Okay, now, here's a little more. We're going to zoom in a little bit here. This is a little bit trickier. This is looking at local extrema. So local extrema means I'm looking at just a tiny chunk of a curve, right? And so an example might be, let me just draw an example here in red. It might be that I'm looking at a curve that's doing something like this. I have endpoints. I have a critical point up here. And then it's like, well, where is the local min, the local max? And so if you look at this curve, you can see that this point up here at the top, that would be the max. And down here would be the min. So these endpoints can be maxes or mins. So what happens is you need to actually test these values to find out where are they. Literally substitute them into the equation to find out what their value is. Then you need to also plug in whatever critical points you get, and then you're just going to rank them. Like which one's the lowest, which one's the highest. So let's practice. So here's our equation, and here's the value. So from 1 to 3. And these intervals must be closed. You can't have, you're going to test your values on the open interval, but these intervals must be closed here to have that, because it has to be defined, right? You can't have the ends be undefined, because then it wouldn't make any sense. All right, so then we're going to do our same techniques. First derivative, set it equal to 0. Here's the first derivative. Set it equal to 0, and then I get my critical point is 3/2. First of all, make sure that that value is in this interval. If it's not in the interval, we don't care. So it's 1.5. It is in here. So now I'm going to evaluate 3 points. I'm going to evaluate 1, 3/2, and 3, and see which is the highest, the top value, which is the lowest value. So I'm going to start here. So f at 1, I'm plugging these into the original equation. So f at 1, literally plug it in, and I get 0. Plug in 3, I get -2. And then plug in this critical point, and I have to do a little fractions here, and I get 1/4. So you're looking at these values. So just look at those. Which one is the highest? Which one's the maximum value? Right here. So then 3/2 is the max. This is the max right here. And then which of these is the lowest? Right here. So 3, that is the min. In this little interval, we have the one that's the highest and the one that's lowest. Okay? Let's look at another example. Here we have our function, x squared minus 3x to the 2/3. Ooh, well, remember 2/3 is the cube root of x squared. So hopefully that's not going to give us too much grief. And here's our interval, 0 to 2. Step 1, take the derivative. Well, you know how to do this. The derivative of x squared is 2x, and the derivative of 3x to the 2/3 is bring the 2/3 down, and notice that 3 and this 3 are going to cancel. So I'm left with 2. -2. And then we subtract 1, x to the -1/3. I'm going to rewrite this so we can work with it. So this is 2 minus 2 over the cube root of x. So this is my derivative. Now you're saying, I don't know how to work with that. Well, we'll get there. We're going to simplify this a little bit, because this is two things here. I want to make it one fraction, and I do that right here. And then again, we're going to find when is this a critical point. So we're going to see when is that numerator equal to 0. You'll notice that you're going to say, well, wait a second. If I plug in 0, that would be a critical point. We're already using 0 for something else. That's why they put that here. So we don't need to consider 0 here. We need to consider points on the interior of these two. So we're not looking at 0. So we then, in that case, since we can ignore that being 0, we're just going to set that numerator equal to 0. Now I've simplified it here. X times x to the 1/3 is x to the 4/3. All right. Divide by 2. Move this over. X to the 4/3 equals 1. That gives you two solutions. That's the cube root of x to the 4th equals 1. Well, x to the 4th, the cube root of 1 is 1, and x to the negative 1 to the 4th is positive 1, and positive 1 to the 4th is also positive 1. So cube root of either of those is 1. So these two here are our values. Now notice this value, this negative 1, is not here. It's not in that. So are we going to consider it? No. We're not going to use that one. So our point we're going to use is 1. Is that in this here? Yes, it is. So we're going to look at 0, 2, and 1. So going back to the original equation, which is here. Remember, we're not looking at the slopes. We're looking at the values of the actual function. Plugging in 0, I get 0, obviously. Plugging in 2, 4 minus something weird here, some kind of decimal thing's going to go on there. And then, although cube root of 4, this is going to be some kind of a positive value here. And then at 1, this is negative 2, right? This is 1 minus 3. So then we look at these and we say, well, which of these is the lowest? And we would say, oh, here it is right here. Which of these is the highest? And it would be this one, whatever the decimal value is here, which I don't have off the top of my head, but you could certainly put it in your calculator and see. And so then this would be the max, and this would be the min. Pretty straightforward with those. So again, take the derivative, set it equals 0, find your critical points, and make sure they're in the bounds that we're looking at, in the interval that we're looking at. Then evaluate both parts of the interval and whatever critical points you have. And then just literally make a chart or a table or just sort them, high to low, and then those are your values.